Hello, my name is Christopher Hyatt, and this is Magnetic Braking with Faraday. First of all, as a brief introduction, the purpose of this lab is to explore what happens to a magnet as we drop it through a ring of aluminum foil or any kind of thing that can carry current. The fundamental principles we'll see in this lab are Faraday's law, the magnetic force, Newton's third law, Ohm's law, and Lenz's law, some of which you can see in the image in the top right, where the negative sign is Lenz's law, and then the inf equaling nd phi dt is Faraday's law. And as a brief preview of the main result, we'll see that this current caused by change in flux is going to slow down a magnet falling through a tube. As the experiment, you can see here in this video, we dropped a magnet through a tube of aluminum foil. You can see from the initial drop that the magnet falls much slower than you expect it to. The initial conditions are that the magnet is held completely at rest and then dropped through the tube. And then the system is the aluminum foil, the magnet, the earth, and everything around it, and there are no surroundings. The experiment logistics can be seen here, and they will be further used in the coding later. The most important thing here is that the average experimental fall time was 1.622 seconds, and the calculated through coding was 1.724 seconds. Next up is the code. Here we can see the coded model with the graph showing the acceleration slowing to a crawl as the magnet passes through the tube. And then we can see the tube in the image on the left, where we can see the counterclockwise as current as the blue, and then the clockwise current as the red, and then an arrow pointing downwards to show the direction. Similarities and differences between the data and the model are that the model doesn't account for friction, and sources of error include user error in timing the fall duration of the magnet, and then the frame limit that doesn't allow me to get a super specific time. Here you can see the important parts of the code that we had to edit ourselves, where you can see starting with the first step, we just define all of the constants regarding the experiment that were listed earlier. We see the defining of dipole B, and then we see the calculation of flux. And then here we can see the second step of the code, where we calculate the force of gravity. We calculate the magnetic field at each ring, and then we calculate net force. And then we calculate we provide an update for velocity and position. Next up, we have interpreting the simulation. Question 1 is the intensity of the coloring on the tube indicates the magnitude of the current flowing through each ring. Red and blue indicate current flowing in opposite directions. Which color corresponds to clockwise and which counterclockwise? Which we answered before. Because in our experiment we always drop the magnet with north facing up, the blue current runs counterclockwise and the red current flows clockwise. Next, what happens to the dynamics of the system when you flip the magnet? Dynamically, the system acts virtually the same. The only difference is that the blue current would run clockwise and the red current would run counterclockwise to counteract the opposite flux with equal magnitude. Question 3 is, how does the total time in tube of your real-world system compare to that of your computational system? How could the computational system be more accurate? The real-world system is slower than the computational system. This is probably because of friction, and friction could be incorporated into the computational system for increased accuracy. Question 4, how does the shape of the velocity versus time plot tell you about the forces acting on the bar magnet? The shape of the velocity versus time plot shows us that the net force on the magnet during its passage through the tube is close to zero, as the current induced in the aluminum foil creates a magnetic force on the magnet that counteracts the gravitational force. What if? What if the resistivity of the conductor was reduced as close to possible as zero? How would the dynamics change? The current opposing the gravitational force would be unhindered by resistance, causing the magnet's descent to be slowed extremely. What if holes or slots were cut? The magnetism would speed up in areas with holes or slots as current would be unable to flow around the magnet in those areas. In conclusion, when you drop a magnet through a tube of material where current may flow, it will slow the magnet as a result of Faraday's law.